Good afternoon, participants. Welcome back from the lunch break. Hope all of us had a very good lunch here in the hall, and wish also the same to all that are online participating with us. We will start this afternoon session. In this sixth session of our Congress, we will have four presenters, and this will be moderated by Mr. Michael Mayer and Dr. Michael Mayer and Dr. Keiji Yoshimura. They will introduce to us the topics and the participants. Let me say a few words regarding our great moderators. Mr. Michael Mayer, he is scientific director at Filk, Germany. He is responsible for all research activities and scientific work. Mayer received his doctorate from Technical University of Dresden. He worked for various companies, including head of product development at Hacker GmbH. He is co-author of 5 patent applications. These are few of his rich experience that I can mention here. While coming to Dr. Keiji Yoshimura, he's obviously from Japan, Director General for Japan Laser and Laser Products Industry Association. He is also Vice President of the Japan Association of Laser Technology, PhD holder in agriculture about collagen utilization, worked for more than 35 years at Tokyo University of Agriculture and Technology. Allow me now to pass the floor to our great moderators. Over to you. I'm sure you are online. Thank you very much.
Thank you very much. I hope you hear us. Thank you very much for this nice introduction. And thank you also to Keiji to co-moderate with me this session. We decided that I will take over the first 2 speakers, and he's responsible for the second 2 speakers. So I would like to introduce our first speaker for this session. It's Dr. Ramakrishnan Prasad Mupa. Originally, he's born in India, and he has received his PhD in zeolite and molecular sieve catalysts from the Indian Institute of Chemical Technology. He worked as postdoctoral researcher at different universities in Europe and Asia, and joined PTD Hexion company in 2012. And currently he's working as senior scientist for R&D at Smith & Zoon in the Netherlands. He's responsible for 14 publications. He's written 14 publications and responsible for 9 original patents. The topic he's talking about, we heard a bit about this, but I think different things we hear about this now, is phenolic monomers in aromatic synthons and their influence on leather, restricted and pending restricted compounds. So it's up to you, and we are curious about your talk. Mr. Mupa, are you online?
Yes.
Okay.
Are you hearing me?
Yes, perfect.
Thank you. Thank you for the excellent introduction. I'll be sharing my screen. Good afternoon. Good afternoon to all brothers and sisters of leather community around the world. A very warm welcome to IULTC Congress, and specifically to my presentation. I am Dr. Prasad from R&D Department of Smith & Zoon. Myself and my colleagues at R&D Department, we develop innovative products which have positive value on the leather. It was at the beginning of this year, we have a call from one of our customers to discuss an important issue. I was present from the R&D side in that call, and the question from the customer was about the bisphenols. So the customer requested, could you supply the bisphenols-free products? And that triggered us to do more research on this topic of bisphenols. And here we combined it as phenolic monomers in aromatic syntones. I would imagine that many of the audiences who are here also have confusion or required more clarity on the phenolic monomers and specifically bisphenols. So title of my project, Phenolic Monomers in Aromatic Syntones, the Influence on the Leather. So what are monomers? Basically, syntones are condensation polymers, condensed polymers. So they are formed by phenol, phenol sulfonic acid, and bisphenol S by condensation with formaldehyde, where urea is also optionally used. So these monomers polymerize into a polymer to form a synthetic retanning agent or synthone. So as you see on the left-hand side, in an ideal polymerization, all the monomers will convert into polymer. That is in the ideal case. While in the reality, some of the monomers, very little amount of monomers, are unreacted and left in the end product as monomers. So what are the phenolic monomers that we are discussing? As you see, this slide presented the chemical structures: phenol, phenol sulfonic acid, bisphenol F, and bisphenol S. In leather chemicals, till the beginning of this year, we are only familiar phenol, which was mentioned as rest monomer, while the other in the leather chemicals literature are considered as intermediates. And that is true in a sense, because we start always with phenol and react with sulfuric acid or oleum, and then followed by condensation with formaldehyde and urea. So therefore, that makes sense. But the bisphenol F and bisphenol S, little extent phenol sulfonic acid, are synthesized or produced in a very big amounts to form performance plastics, and which are used in large amounts to produce the performance plastics. And in fact, even they are used as bisphenol A alternatives. And obviously, the people who work with these chemicals care about the health effects of these monomers. So why is this phenolic monomers research important? Just now I mentioned the hazardous classification level of these monomers is a well important aspect for the people who are working with them. And the second, efficiency during the retanning. When the synthone is bought, if it has a small amount of monomers, let's say 5-8% or 2-8%, and that is kind of undesirable. The polymer is the one which is responsible for the retanning, while the rest of the monomers are no active or very little active on the leather. So that is with respect to the efficiency, it is important to have the more polymer. And then the last is the effect of haptics and the leather properties. Then what did we investigate in this study? So the amount of monomers in the synthones which are available across the market. And the second topic, what is the effect of the phenolic monomers on the haptics of the leather and also the properties. And the third aspect, I would like to give a summary on the regulations that exist on the phenolic monomers today. So the methods are used for this study. HPLC was widely used to determine the phenol, phenol sulfonic acid, bisphenol S and bisphenol F. In fact, bisphenol S and the F were analyzed at external institutes like Philk, CTC, and Ars Tintoria, while phenol and phenol sulfonic acid were mostly analyzed in-house. And we also widely used the X-Trite SP60 for the light fastness and heat alloying measurements. And the leathers tested with mostly internal standard methods. For the leather assessments or leather performance were done with wet-end recipes, while the leather properties were studied by single component recipes. Okay, the results. This slide presented the amount of phenolic monomers that are present in sulfone synthons that are from across the market. So sulfone synthons here means they are condensed products of phenol and bisphenol S with formaldehyde where optionally present urea. So then here, as you see in the table, the first column, which is a marked column, is the bisphenol S that is present in the sulfone synthons. As you see there, so the amount is ranging from 2 to nearly 6 to 8%, which is relatively high in all sulfone synthons. And then comes the right-hand side, 2 columns, phenol and bisphenol F, which are very low, only in the range of 100 ppm, except one, but it's mostly the phenol and bisphenol F are very low. And phenol sulfonic acid, which is not that important with respect to the safety aspect, so I will not go into so much details into it. And in this table also one synthon SC0, which is included for comparison reasons, which is a phenol condensate, which doesn't have any BPS, also have less free phenol and less BPF, simultaneously having very low BPS. Then this slide presented the amount of monomers in phenol condensates, which are basically phenol and phenol sulfonic acid with formaldehyde, where urea is also present. So these condensates have very low, due to their chemistry, very low bisphenol S. On the other hand, they have relatively big amounts of phenol and BPF as monomers. So this slide presented the trends of the amount of phenol and bisphenol F in ppm in the phenol condensates. As you see in the slide, they are always in proportional relation. So when phenol is low, bisphenol F is also low. So that tells us that if phenol is optimized in the phenol condensates process, then automatically the phenol F will also be reduced. Then I will be speaking in this slide about the uptake of phenolic monomers. So the uptake of the phenolic monomers, phenol, phenol sulfonic acid, and BPS and BPF are mostly connected to the solubility of the monomer in the water. So the more the solubility, less the uptake. So as you see the last row, BPS and BPF has very low solubility in the water, below 1 gram per liter, and which has above 90% and almost 100% uptake on the leather. And with phenol, which has moderate uptake on the leather, and similarly also PSA. So here, this graph presented the light fastness of sulfone synthons, where the BPS weight percent in the sulfone synthons across the market on the x-axis, while the grayscale values on the y-axis. As you see it here, with the increase of the bisphenol S amount in the cell phones, the light fastness was decreased from almost 4.5 to 2.5 grayscale value. And SC0, as I said, which is a non-cell phone condensate, has 4.5 GS value. Then similarly, we also checked how the phenol that is present in phenol condensate influences the light fastness of the leathers. And similar to the BPS, also phenol has inversely proportional relation to the light fastness. So with the increase of the phenol amount, the light fastness was decreased. Unfortunately, we don't have a lot of points between 2000 ppm to 5000 ppm, but with the limited number of samples, we can see the trend with the decrease of the light fastness. Then actually to confirm the effect of bisphenol S, we have spiked the symptoms with a known amount of BPS, bisphenol S. As you see it here, when we spiked the symptoms with bisphenol S, we don't see the decrease of the light fastness. In fact, earlier we hypothesized that both the phenol and bisphenol S have inversely proportional to the light fastness, but by seeing these results, the phenol and bisphenol S are not the direct cause of the decrease in the light fastness, while some other compounds, which are very likely the intermediates that form during the condensation, have relation to the light fastness. So in the results, leather results, so both bisphenol S and phenol sulfonic acid, when they are lower than 5.8%, we see harder, fuller, tighter, and lighter color leathers, lighter in color leathers. While with above 5.8%, we see clearly harder and more emptier handle. And that makes us to speculate that actually the BPS, due to its low solubility, it is sitting mostly on the surface of the leather and giving us a feeling that it is harder, while actually it is not going inside. So you see the emptier handle inside the leather. Then comes to the phenolic monomer. Actually, phenol is, in fact, tanning very good. So when it is above 10,000 ppm, we have a good fuller and softer leather, which is not desired because phenol also, we are leaving a lot of phenol into the wastewaters, while we see a clearly, when the phenol is above 10,000 ppm, it has good tanning effect. And below 1,000 and in between 1,000 to 10,000, we don't see any clear effect, which is sometimes visible and sometimes not visible. Then I will make a overview on what actually the regulations are speaking about these monomers. First, the phenol sulfonic acid, which is only classified as corrosive at this moment, and which is low acute toxicity based on these LD values. And there are no regulations on the restrictions on the phenol sulfonic acid, at least this, which is relatively low with respect to the SHE aspect compared to the phenol and bisphenol S and F. The second one is phenol. Phenol is, of course, as classified as high acute toxic. There are no regulations on the restrictions now, but which is present right now in the ZDHC MRSL 2.0 list for textiles. And so therefore, a restriction can come soon. And if textiles put a restriction, then it can also happen for the leathers as well. However, there are already brands, consumer brands have been asking for the products with very low free phenol. Then comes the bisphenol S and bisphenol F. They are actually very low acute toxic. And right now there are no restrictions present on the limitations, but ECHA, European Chemicals Agency, is the proposal is under assessment for the reprotoxic 1B as reprotoxic 1B, which means that these compounds are toxic to the reproduction health. The research studies are also proving that the BPS and BPF are also comparable or even more toxic as bisphenol A. So that means there are potential chances that it can become a regulation at ECHA in coming maybe 5 years. But until that moment, there are no regulations for the chemical producers. However, there are always chances that actually consumer brands can ask for the low bisphenol S amounts. Then that brings to my conclusions. So as just now I said, bisphenol S is relatively in big amounts in the sulfone synthones, while phenol and bisphenol F are in relatively big amounts in phenol condensates. Uptake, unfortunately, BPS and BPF have very big uptake. And phenol and BPF amounts are proportional in the phenol condensates. Then we have seen both phenol and BPS are good markers to follow the light fastness, although they are not directly related to the decrease of the light fastness. We see, based on our study, phenol condensates with very low free phenol found to be better light fast than sulfone condensates. And we don't see a big effect of monomers on the heat alloying. While all the phenolic monomers that are studied here does affect the haptics and wastewaters negatively. So they are not desired. So the takeaways from my presentation, sulfone synthones have a challenge with reducing the amount of bisphenol S in them. Then the phenol condensates, the phenolic condensates producers also have a challenge to reduce the phenol and bisphenol F. However, there are phenol condensates with very extremely low phenol and BPF in them. So there are a lot of my colleagues who have contributed to this study from product management and sales. Arnaud, Stefan, Martin, and Job helped with organization of analyzing a big number of samples. Then Heriana, Rob, Tinu, Marek from the in-house analysis group, Petra, Lilian, Anouk from the R&D for the support and also organizing everything. Then the last group, Art, Kainan, Sarah, Tomaso from the Leather Research Center, who have helped to conduct all the applications. Thank you for your kind attention, and thank you for the opportunity to present this work at IULTC. Thank you.
Yes. Thank you very much, Dr. Prasad, for this nice talk and for this nice presentation. We will answer the questions after having had all 4 talks. So we will directly switch to our next presentation. The next presenter will be Mr. Jibo Zhu from China. He is PhD student in biomass chemistry and engineering at the Department of Biomass and Leather Engineering in Sichuan University in Chengdu. And his research area is the cleaner production of the leather industry. A topic he will present, which is nearby this, what we heard before and also this morning. We will talk about a novel preparation of formaldehyde-free melamine resin and its retanning behaviors investigation. The floor is up to you. We are curious about your presentation.
Thank you, Professor, and good afternoon, everyone. Thank you, Professor, and good afternoon, everyone. Thank you, Professor, and good afternoon, everyone. It's my pleasure to give a report here. The name of my report is A Novel Preparation of Formaldehyde-Free Melamine Resin and its Retanning Behaviors Investigation. I will introduce my research from the following 4 parts. Firstly, the background. As we know, melamine resin has many applications in our daily life. such as laminates, coatings, textile, and paper, moss, leather. It is cost-effective and shows good thickening effects. However, and good thickening effects, building in selective building property when applied in laser retaining. However, its further application is hindered by the formaldehyde issue. Extensive work has been done in the past few years to address the formaldehyde contamination in melamine resin. Many environmentally friendly reactants such as glutaraldehyde, fusel, and some natural feedstocks contain starch. Tanning have all been tried in the synthesis of formaldehyde-free resins. These synthesis products have no health issues, but they are mostly in the laboratory development stage and still suffer from several obstacles such as lower aldehyde activity, much higher cost, or complicated procedures. Moreover, the reaction between these compounds with melamine must be self-initiating process to improve the water solubility. This process may decrease the positive charge of melamine resin and finally influence the absorption of the following anionic phytolicquid agents and dyestuffs. With the development of leather industry, there is a need for amphoteric melamine resin. So in our work described here, a new formaldehyde-free melamine resin, MGE, was prepared through a novel synthesis strategy. Here, melamine was firstly bound with lysine by glutaraldehyde. Lysine is a natural available resumable feedstock and contains a carboxyl group and two amino groups in its molecule. The amino groups make lysine very easy to bond with melamine by glutaraldehyde. Through this approach, lysine can not only improve the water solubility, but also confer amphoteric properties to final melamine resin products. Moreover, lysine supplies good compatibility with collagen fibers, thus may result in a higher absorption of synthesized retaining agents. Here is the synthesis process of MGE. Melamine was firstly reacted with glutaraldehyde to get the intermediate MG, and the lysine solution was then added to the system to prepare MGY. Finally, ethylene glycol diglycid ether, EGDE, was further used as a cross-linker in the synthesis of formaldehyde-free melamine resin. EGDE is one of the most important commercial compounds. It has volatile reactivity and can be served as a substitute for the polycondensation stage to realize the cross-linking process. After preparation, the chemical structure of prepared MGE was characterized by FTIR and carbon 13, NMR. As illustrated, the characteristic peaks of MG, MGY, and MGE can all be found in the spectrum, indicating the successful synthesis of MGE. It is notable that the peak at 174 ppm was assigned to esters generated from the reaction of carboxyl and epoxy groups. The higher intensity of this peak suggests that the cross-linking mainly took place between these two groups. Additionally, the average particle sizes and the potential of different resins were also determined. CMS and CML here were two commercial melamine resins used as comparison, and MGE 1, 2, 3 were synthesized using different amounts of EGDE. It can be seen that CML exhibited the largest average particle size of 483 nanometer, and the other four resins showed similar average particle sizes of 150 to 224 nanometer. The rate potential of MG increased progressively with the increasing dosage of EGDE. Combined with the carbon 13 NMR analyzed results, it can be concluded that the consumption of carboxyl leads to the decreasing of negative charge and finally resulting in the increase of the potential. The higher electrode point of MGE is important in the laser retaining process It can improve the bonding rates of subsequent anionic fat-requiring agents. Finally, the retaining performance of MGE were also investigated. It can be obviously seen that the absorption of MGE was up to 77%, significantly higher than that of the other reasons. It could be suggested that the introduction of lysine in MGE established a biomimetic structure to collagen, which promotes it easily diffuse into collagen fiber system. Meanwhile, the smaller particle size of MGE also created a favorable condition for its penetration in laser. Moreover, MGE was amphoteric and showed a higher isoelectric point. These features can improve its bonding ability with collagen fiber and anionic materials, which ultimately leading a higher absorption rate and of anionic fat-requiring agents. From the results of cream, softness, fullness, and tear strength, MGE showed higher overall performances. MGE contains abundant functional groups. These groups make it more effectively to be interlocked in the structures of collagen fibers. Thus showed a satisfactory fullness behavior. MGE shows an amphoteric property. It can facilitate the absorption and bonding of anionic fat-requiring agents through the regulation of charge, thus leading a better performance. Here is the conclusion. In this paper, melamine was firstly bound with lysine and a novel formaldehyde-free melamine resin MGE was prepared through exposé cross-linking strategy. Due to the introduction of lysine, MGE showed an amphoteric property and a high storage ability. MGE can facilitate the absorption of fat-requiring agents and reduce the release of cream. MGE showed better overall performance. Okay, the above is all of the content of my report. And I'm sincerely grateful for my supervisor, Dr. Xue Pingliao, other co-authors, and the conference organizing committee. And thanks for everyone here listening to my report. Thank you. That's all. Thank you.
Thank you very much for this nice presentation and for this nice summary about your research.
We can proceed to the next presenter if he is there, Mr. Saggaudemsi.
Mr. Tugo hold an MSc degree in chemical engineering from Addis Ababa University, Addis Ababa Institute of Technology, Ethiopia, and Central Laser Research Institute, India. Through a sandwich program, he has been working in Laser Industry Development Institute, Ethiopia, and the laser manufacturing technology and laser technology directorate. He is also involved in teaching as guest lecturer in TBT centers and the Addis Ababa Institute of Technology School of Chemical and Bioengineering Department. The next presentation is about the paper entitled Extraction and Purification of Collagen from Tannery Fleshing Waste, a way forward for sustainable laser manufacture. Mr. Trugo, go ahead.
Okay, good afternoon. I am from Ethiopia. I'm Damse. My title is Extraction and Purification of Collagen from Tannery Fleshing Waste. That is a way forward from sustainable laser manufacturing. In our discussions, it is including the content is just like this, and I proceed to directly for the introduction part. Laser industries have a great role in economic, and that is connect from the rural to the fashion world. So laser industries has a great role, but it produce a pollution from these industries. The main principles operations are BMOS, tanning, and post-tanning, and flashing. From here, we concentrated in the B mouse. It is unhairing and liming. This role is breaking the cysteine bonds by the routers of Prasad in 1990. This contribution high load learned in B mouse operations in the liming and unhairing process. The estimation data in B mouse 800,000 metric tons solid waste are generated from here. So this is a huge challenge in BMOS operation process. So we concentrated in among of them is flashing waste that is disposed in environmental. This faces a huge burden properly to manage it. From it, an estimate in Kanagaraja says 1 ton of rawhide is processed to generate from 0.6 up to 0.7 ton of solid waste are generated. From it, 60% of solid wastes are contributed in the flashing wastes. During here, the main, so we think that it changed to value addition, this waste to wells or other byproducts. So when we concentrated here, we such writers or investigators, we can see one of the resource from here is collagens. So collagens are many writers right here for this waste products. From here, tanneries changes from 50% to changes to lasers, and from 10 up to 15 wastes are flashing wastes. This flashing waste has collagens have this content, so we concentrated here. So the application collagens are so many types, that's biomedical application and others. There are 29 type of collagens, which is the biochemistry sequences in the glycine, proline, and in the XXXVI sequences. These XY sequences in the collagen parts, 10% is glycine, proline, and hydroprolines. This is 10% contributed. So flashing wastes are also another raw material for glue, gelatin, and feeds and fertilizers. So we understand here, we hypothesize that extract collagen using acetic acid. So new opportunities that will lead to high value realization with the roadmap of business that is used for applications. When we prepared this type of hypothesis, we use the raw materials, the lime flashing and the salts, acids, and is another equipment is the tannery machines, laboratories, analytical instruments, UV, CD, FITARA, and set pages. And another we use characterizations, that's approximate analysis by standard methods of the moisture content, fat content, and the collagens. So how to prepare this, our researches, we prepare the flashing waste just like this, since flashing waste have limes and sulfides. So remove towards this, we follow these approaches. So after we extract, we predict that we use the characterization of collagen from lime flashes. That is approximate analysis, CHNS elemental analysis, SCDS page, FATR, and CD spectroscopy, and thermal behavior of the collagen when after extracted. So this is our extraction method. When we come to the result and the discussion part, the approximate analysis are composition and analysis. The amount of fat is from flashing waste is around 6.5. Moisture is just like this. And the hydroxyproline is just like this. And the collagen of this are extracted in around 12%. When you come to the LD parties, we extracted around 12 points that, and we use the dried collagen obtained around from 6 points from 50 grams. and the collagen extract efficiency is around 85%. So when it comes to the elemental analyzers, the nitrogen part is this, the carbon and hydrogen and the sulfide also almost nil. Okay, another character is we should be check whether this collagen is pure or not. So we should be run the SDS pages as sodium disolate, sulfates, polyacramides, and gel electrophoresis. So when you check run for this our samples, we get this type of proteins. That is collagens around from 220 and 130s. This shows that our extract collagen shows high pure. So our extract collagen shows good results. When another method of checking is that the FETA analysis. So we check in here also, we get this results. So our collagen is pure extracted. So we check by 2 times. So our extract collagen is pure. So whether this collagen is second structures or not, so we run circular dichromosome spectra. So we get the net triplical helical structures at 220 nanometer and at 198 nanometers. So these extracted purified collagens also a second structures we observed by this 222 nanometer and 129.5 nanometer. So our extracted collagen is that is second structures. Another checking method is the thermal melting transition of collagens. So we observe in the thermal melting points. For the first derivative of this is that is 47. Collagen denatured temperature is around 40 degrees centigrade. So our results also match this checking of method of experiments. So when it comes to our conclusions, laser industry need to find a solution from waste management. So waste has a source of product generate that's the revenue. So we don't think that always waste. So we should be changes waste to getting an income. So extraction method is at a low costs. Another is extraction and characterization of the value protein collagen from lime fluctuations is so high qualities and pure, and we get second structures and thermal stabilities also. So when we checking the tropical high pure and it is native tropical helical structures, and this lime flashing waste can be considered as a source of high pure collagen, and that is in the revenue streams. So we consider that these collagens used as for wound healing and tissue engineering and cosmetics are other food industries. So finally, I want to say, acknowledge this, our papers for LIDI, for sponsor for to attend the IULTCS and other work partners, Professor Madans, Dr. Ganesh, Danish Kumar, Aaron, and Ramesh, and Dr. Shagga from Ethiopia. And I would like to thank you. Thank you very much.
Mr. Tugo, thank you very much for interesting and nice presentation. Solid waste from leather industry is a significant problem to achieve sustainable leather manufacture. Thank you very much. And the former presenter, Mr. Wang, is Mr. Wang joining? No?
Is he available in between? I don't think so.
Yeah.
I don't see him on the list.
Oh.
So maybe we should proceed with the questions and answers. So our first question is to Jibozu. Good presentation, good idea. I'm sure the melamine lysine moiety is quite stable. Can glutaraldehyde can be released? It's coming from Jochen Ammen. He talked this morning. Maybe you can answer this question, please.
Okay, thanks for your question. That glutaraldehyde is existed in the retaining agents, and when after retaining the laser, it is still excited in the laser, but we haven't it can be released from laser. We will be exploring it in our later work. Thank you. That's all. Thank you.
In between, may I ask you another question? It seems to me that lysine maybe is a bit cost intensive. Could you comment on this? It is very, very expensive.
No. Lysine is cost effective, and the EGD used in our experiment is very little. So it does perhaps it is cost effective for EGD for our final products.
Thank you very much. So I have a question to the last presenter, Demissi, if possible. You showed that the collagen you extracted is native, correctly? Is this correct?
Yes, it is correct, sir.
Wonderful. Do you had any troubles with the fat content?
Actually, flesh waste is a difficult waste because the content is so much. The adobes part is contain liming and sulfide. So when we remove this part, we should be serious follow, and we should be optimized how to extract the collagen from here. So we should be check whether this liming and sulfide properly remove or not. So it is this challenges faces. The other is the homogenization part. When we make homogenize, the fatty substances affect the tendency of extraction of collagen. So we face just like this problem.
And the last question to you from my side, you mentioned that you would like to use this material for food or for medical applications. In European Union, there is a hard regulation about this. Is this similar in your country, or how is this handled in your country?
Actually, we try to, for preparation for a scaffold, after a scaffold, it takes, we apply in the clinical should be study. So we have a short period of time to apply that part. It takes another study. So we stop here. But during the preparation of a scaffold for applying of wound, we got good results from that collagens. So we didn't apply others for cosmetic or feed, and others we didn't apply. So, but we try to apply for the wound healing.
Wonderful, thank you. Keiji, do you have any questions?
Yeah, hi. My question is Mr. Tsugo. In Japan, most part of the waste from lime fleshing effectively utilized for collagen and gelatin. I think you had a better result to waste after turning, especially finished leather, most difficult. I hope.
Sorry, pardon.
Yeah. My hope, I think you had a better result to waste after turning, especially finished leather waste. Because in Japan, most part of the waste from lime pressing, it's effectively utilized for collagen and gelatin. Finished leather is more difficult to utilize or utilized. My opinion.
Okay. I think the big challenge in a case of what Segaf Demesi presented is that it's a...
Sorry, sir, I didn't get your questions.
To upgrade some products with this. Okay, I think we have no further questions and we have no further comments, I think. Thank you very much to the presenters, and I hand the microphone back to the professor who presents now, I think, the certificates, if I'm right.
Thank you very much.
Thank you. Thank you. Thanks a lot to our moderators and also to presenters. Really, that was a great scientific research that you have shared to us, which we benefited a lot. With that, we end this sixth session of presentation. We will break for a few minutes, but before breaking, I would like to invite our head of administration and budget for some housekeeping issue. Madam, over to you. As you see, it is being displayed for the presenters. Very sorry. Yes. Yeah, these are certificates to be soon to be mailed to the presenters. Thank you very much. Can we come in, our friends? I think to complete our today's activities, we are remained with only one last session. But before starting that last session, we have our known friends for that energizer, which will give us more oxygen to tackle the last part. Over to you.
Hello, everyone. We are so happy to see you again. We are here to give you a little bit energizing stuff, and we'll be back to your meetings.
Last time we did breathing technique and flexibility. Today we will work with some toning and strengthening exercise for 10 minutes, just to motivate you and to enhance your oxygen level. Okay, thank you. Ready? Relax. Okay, shoulder wide. Okay, next, shoulder wide. Then this wide, abdominal in, choose high, walk straight, up, and forward. The whole rest. When you go up, exhale. 1, 2, equal. 3, equal. 4, this is for shoulder exercise. 5, go. 6, go. 7, go. 8, slowly. 9, 10, and relax. Breathe in, breathe out. Breathe in, breathe out. In, breathe out. Okay, like the first one, like this. Yes. Push it forward, front, 1, yes, 2. This is for chest. Up, 3, first 5, 4, good job. 5, 6, 7, 8, nice, breathe in, breathe out. 9, 10, relax, relax, relax. Breathe in, then breathe out. Breathe in, then breathe out. Nice. All like this. Pull it. This is for back. Yes. 1. When you work out, exhale. Yes. Go. 3, 4, 5. Good job. 6, 7, 8, 9, 10. Relax. Relax. Breathe in, then breathe out. Nice. Breathe in deeply, then breathe out. Breathe in, breathe out. Nice. Yes. Flat. Up, 1. Good job. Exhale. Exhale. Go. Exhale. Yes. Push it. Nice. Good job. Nice. Nice. 5, 4, 3, 2. 1 more. Relax. This is self massage. Huh? Relax. 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 Breathe in and breathe out. Breathe in and breathe out. Nice. 1 more. Breathe in. Breathe out. Good. All like this. Then pull it. This is for lower back. Yes. 1, 2. Breathe in. Breathe out. 3, 4. Yes. 5. Abdominal in. Yes. 5, 6. 7. Good job. 8, 9, and 10. Then breathe in. Breathe out. Breathe out. Yes. Breathe in. Breathe out. Then hold it like this. Then chicken wing. 1. Good job. Come on. I think you like chicken wing. Go. 2. Yes. This is chicken wing exercise. 3. Come on. 4. Good job. 5. Nice. 6. Nice. 7. Good job. 8. 2 more. 9. 1 more. Yes, relax. Breathe. Then breathe out. Breathe. Then breathe out. Yes. All like this. Come on. Come on. This hard. Yes. Make it small circuit. Small circuit. Yes. Small circuit. Over. Yes. 1. 2. A little bit go down. Squat position. Squat position. Go. 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 5, 4, 3. Stretch you out. Stretch you out. 2 more. 1 more. Then relax. Breathe in. Breathe in. Then breathe out. Breathe in. Then breathe out. Go. The same position like the previous. Same position. Then reverse. Yeah. The first one is forward. Then forward. Come on. 1, 2, 3, 4, 5, 6, 7, yes. 8, 9, 10. Then relax. Breathe in. Then breathe out. Breathe in. Breathe out. Good job. Nice. Relax. 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 Position. Out like that. Then big circuit forward. Big circuit. Go. Wow. Yes. Stretch your arm as much as you can. Go. Yes. Big circuit. Come on. 4, 5, 6. Come on. 7. Good job. 8. Nice. 9. Big circuit. 10. Then relax. Go. Go. Breathe in. Breathe in. This is stretching. Also strengthening your muscle and your thought. I think everybody dreams like abdominal and core muscle, right? Yes. Keep going. Keep going. Keep going. All like this. Push it right and the left. Right and the left. Right and the left. Go. 1, 2. Got this. Come on. Come on. Come on. Good. Breathe in. Breathe out. Breathe in. When you go up, breathe in. When you go down, breathe out. Breathe in. Breathe out. Breathe in. Relax. 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 Still, we take upper body only. We'll go to lower body. 2 minutes. Okay? Ready? Ready? All like this. Yes. Like this. Yes. Like this. Yes. Bring your leg up. 1. Yes. 2. Yes. 3. Yes. 4. Yes. 5. Good job. 6. Come on. 7. Nice. Come on. Up. Yes. 8. Come on. Up. 1 more. Up. Yes. Relax. 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 When you relax, you should take oxygen. Easy. Out. Easy. Out. Yes. Life, right? So breathing, breathe out is very important. Okay, next one. And like this, then a little bit twist. 1, 2. Yes. 3. Finish twist. Opposite. 4. Good job. Yes. 5. Keep going. Opposite. Yes. Opposite. Yes. Come on. 4 more. 3, 2, 1 more. Good job. Relax. Relax. Breathe in and breathe out. Breathe in and out. Nice. And side. Side. Up. Up. 1. Up. 2. Up. 3. Go. Yes. Yes, 6. Yes, slowly, slowly. As much as you can. You can like that. Go. 2 more. 1 more. Yes. And relax. And relax. Good job. Good job. Good job. Good job. Nice. Last, breathe in. Breathe out. When you go up, breathe in. When you go down, breathe out. Good job. The last exercise. The last exercise. Hold like this. Then boom. 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 Back. Yes, this is for lower back and hamstring. Go. All like this. Boom. 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 Good job. Come on. Yes. 5. Yes. 6. Yes. 7. Yes. 8. Yes. 9. Yes. 10. Good job. Good job. Good job. Then relax. Relax. Shake, shake, shake. Shake, 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 shake. Shake, 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 shake. Everybody shake. Shake. Then relax. One gentle step. Then opposite arm is here. Stretch your arm. Stretch your arm. And your leg. Bring the other leg up. Try to look the floor. Feeling. Go. Up. Up. Then the same one. Change. Yes. Switch. 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 Then cap. Like this. Like this. Like this. Like this. All like this. Then slide your arm. Go up, higher, higher, higher. Then out. When